In this video, I will go over number 2. Joe is 25 years old today, and he plans to retire when he's 67 years old. Suppose he invests $50,000 in an individual retirement account IRA that earns interest at an annual rate of 4.26%. Assume interest is compounded continuously. Look, there's a keyword that we must highlight. Compounded continuously, right? So the equation will be A equals principal times e raised to the rate times t power, because they said compounding continuously. First part is asking, in how many years will Joe double his initial investment? Round to the nearest hundredth. Now we can do this two different ways. We can take a shortcut and just use a doubling time formula, or we can solve an equation. Okay. Since I have this up here, I'll go ahead and solve the equation. But I'll also talk about the doubling time formula, which is gonna be a nice shortcut. But listen, he starts with $50,000 today, but he wants to end up with $100,000. Not he wants to end up with, but he wants to know how many years will it take for 50,000 to become 100,000. So for A, ending amount, I put 100,000. Initial amount, I put 50,000. And I'm going to go ahead and write down the rest. E raised to the R is 0.0426. 0.0426. And t is what we are solving for. Divide both sides by 50,000. You will get 2 on the right side. On the left side, because we got 100,000 by doubling 50,000. So if you divide both sides by 50,000, you will get 2 on the left, and you will have e to the 0.0426t. To bring down that exponent, I'm going to go ahead and take natural log of both sides. So you will have natural log of 2 equals, and the right hand side is natural log of e to that power, but ln and e will cancel out after this exponent comes down. So I think it's okay if you just want to write this as your next line. And to solve for t, all you have to do is divide both sides by that decimal, 0.0426. All right, we need to round to the nearest hundredth. So let me go open a calculator. Okay, so I need to divide natural log of 2 by 0.0426. And that answer comes out to be 16.27 years. So this is a longer method, but on your test, you may not want to spend too much time on this. So if you want to use a shortcut, doubling time formula, oh, my pencil just died. 1 second. All right, so doubling time formula. Doubling time formula is a natural log of 2 divided by r. So if you want to use that formula on your test, that's fine. But that formula is really from just solving for t for any r. Okay? Tripling time, I don't know, maybe I'll ask you to find tripling time. All right, so I should do that. So if I ask you to find the tripling time, then you should do natural log of 3 divided by r, right? Okay, so it's nice. It's only going to take him 16 years, a little over 16 years for his money to become double $100,000 from $50,000. Okay. Estimate the value of Joe's IRA at the time he retires. He did say he's going to work until he's going to retire when he is 67 years old. So how many years is he planning on working? So to find T, I'm going to go ahead and subtract 67 minus 25. Wow, he's going to be working for a while. He's going to be working for 42 years. Or, just wait for his IRA to grow for 42 years. So I'm going to go ahead and find how much he will have after 42 years. Okay, because it's 25 years today, he's going to work until 67. So we're waiting 42 years. So A equals, the principal is $50,000. Multiplying this by E raised to the 0.042 times 426 times 42. Round to the nearest dollar. Okay. So for this part, I will need a calculator. I thought I had one open. Okay. So over here, I will type in 50,000 E raised to the 0.0426 times 42. He's gonna have 299,233. Okay, in his IRA by the time he reaches 67. Okay, that sounds good. Estimate the value of Joe's IRA when he is 63 years old. Okay, so this time our T will be different. If he retires a little bit earlier, instead of 67, if he stops at 63, that's gonna be 38 years, right? Can I trust myself with number? All right, let me subtract real quick, just double check. 63 minus 25 is 38. Yeah, so if he works for 38 years instead of 42, we know he's gonna have less money, right? So let's see. A equals 50,000 times E raised to the 0.0426 times 38 this time. All right, so let's go ahead and type that in. And the number should be smaller than the before. So if I go ahead and change that exponent to be multiplied by 38, I can see that Joe will end up with 252,350. I'll go ahead and round that up to $52 because the cents is over 50 cents. So 51 cents, I'll just round up to a whole $2. Okay, so that's, just in the 3-year difference, no, not the 3-year, I think it looks like 4-year difference, he had much more money. Like, I think, will you wait if you were Joe? Because he can retire and end up with 299,233 when he's 67. But if he retires about 4 years too early, 252,352, he's losing about what, $46,000, so close to like $50,000. So if I were Joe, I will hang in there and just keep on working. I will not cash out that IRA just yet. Part D says, can Joe, he's done working, Joe just wants to buy a $260,000 RV and just wants to go and enjoy his retirement. But can he do that if he cashes out his IRA when he is 63 years old? Explain. Well, when he's 63, his money is, Well, because $252,352 is less than $260,000, Joe will not be able to buy the RV. So you know what? I think if he just works one more year, maybe at 64 and retire, he'll be able to buy this. But not yet. When he's 63, his IRA is slightly less than the goal amount. So I suggest that Joe works maybe one more year if he wants to buy that RV. Okay, part E. What is the... Oh, well, hold on a second. Oh, well, I already kind of answered it. I was going to say no, but I did mention that Joe will not be able to buy the RV, so that's good. What is the rate of change? So now we're doing the derivative. What is the rate of change in the value of the IRA when Joe is 63 years old? We can do it two different methods. So what we can do is we can find A prime of t. You know what, let me go ahead and write down A of t first. The amount function was this. If you take the derivative of this, I have to multiply 50,000 times 0.0426, and that gets multiplied by e raised to the 0.0426t. So let's find that coefficient. On a calculator, I'll go ahead and do 50,000 times 0.0426, and that comes out to be 2130. 2130 e to the 0.0426 t. So if I want to find how fast his IRA is growing when he is 63 years old, all I need to do is plug in t equals 38. Because when Joe is 63, he spent 38 years investing in this account. So what is A prime of 38? 2130 times e to the 0.0426 times 38. And that comes out to be, and I'll show you another method. 2130 e to the 0.0426 times 38. All right, so 2130 e to the, okay, so that will be, I'll write this number down, $10,750 per year. All right, so what does that mean? Well, did we ask? No, we didn't really. We weren't trying to interpret this, but we can talk about it. So what that means is after or at the end of 38 year, after 63, he's going to have this much more next year. That's the rate of change. His IRA is increasing about $10,000 per year at 63 years, when he is 63 years. So that boat that he wanted, not the boat, but the RV that he wanted to buy, he's definitely going to have enough money if he cash out his money at 64. Okay, so but there was another way of doing this. Remember, for these exponential functions, these continuous compounding functions, we can find A prime of 38 by doing the rate 0.0426 times A of 38. So if you do 0.0426 times the answer from part C, 252,352, 352. If you multiply those two numbers, notice we get the same number, right? Slightly different because I guess we rounded this to a whole dollar amount. But if I round that to a whole dollar amount, I will get 101, well, $10,750 per year. And that's the same as what we got from using that other method above here. But you don't have to do it twice on your test. Just pick one method and do what you want. But this is how you would do a number 2, and you'll have a similar one on your actual test.